Everybody, thank you very much for joining us for this first IEEE Haptics Symposium live stream event. We have a great program planned. I'm one of the general co-chairs of IEEE Haptics Symposium. My name is Visell. I'm with the University of California, Santa Barbara.
Hi, and I'm Greg Gerling. I'm the other co-chair of the event. I'm from the University of Virginia.
So we're going to start with a little just orientation information for the event to let you know a little about the conference and what we're doing. So I'm going to go ahead and share those slides now. There we go. So you can get a lot more information about the conference at the website 2020.hapticsymposium.org. And again, thanks to everybody for joining for this event. As we said, Greg and I are the general co-chairs of IEEE Haptics Symposium, although as we'll say, there are many others that have contributed to organizing the conference. I know that we may have some audience members who are new to IEEE Haptics Symposium, and maybe even some who are new to haptics. So if that's you, really glad that you made it here. IEEE Haptics Symposium has been held since 1992. It's a vibrant interdisciplinary forum of research in neuroscience, perception, engineering, and design related to the sense of touch. It's focused on sharing new advances in our understanding of the sense of touch, and has played an important role in sparking new collaborations and helping us all to envision a future enriched by haptic technologies. The conference has grown in recent years. We reached more than 350 participants at the last conference in San Francisco, California in 2018. The conference is held biennially, and the conference is technically sponsored by IEEE, IEEE Robotics Automation Society, and the IEEE Robotics Automation Society Technical Committee on Haptics. I'm going to turn it over to Greg.
Thanks, John. As you might know, the original plan for the conference was to hold a physical event in Washington, D.C. in March. And we had a little worldwide pandemic that we dealt with like everyone else. And hopefully you all are getting through it well where you are too. So we've made a transition, and we're bringing you this event today. Next slide. We've had a number of innovations for this year's Haptics Symposium. The first is that we created a new journal track in cooperation with the IEEE Transactions on Haptics. In particular, Lynette Jones is to thank for helping spearhead this initiative. This has led to the highest number of paper submissions ever. Second, we have now developed several virtual conference offerings. The first is the live stream video event that you're participating in today, featuring award candidate papers. The second is the creation of a Haptics Symposium YouTube channel where nearly all the authors, which we're very pleased to report, have created 3-minute videos to detail their work, and those are all archived there for your viewing. Next slide. So let's get to the program for today. We have 3 oral sessions to present today. The first is going to be moderated by Karon Maclean, the second by Manuel Cruz, and the third by Ed Colgate. And we're very happy to have them helping us in this aspect. We'll move to a works in progress session, an awards ceremony, and a future conferences preview announcements. And we're hoping the entire event will take about 2 hours, 2.5 hours in duration. Next slide. Each oral session will have 5 video presentations. At the end of that, we'll have 18 minutes of Q&A with the moderators who I mentioned. You can pose questions to Slido, and we strongly encourage and hope you do pose questions to Slido. All you have to do is go to slido.com and you type in this code 69159. And if you want to take 1 second now to jot that down, that's the number 69159 to ask questions.
There's also a link to that page in the video description below.
Excellent. Next slide. We have several social media options that we encourage you to follow, in particular Twitter during this event, hashtag IEEE Haptics, as well as Facebook and YouTube as you're watching now. Next slide. we've got so many people that we would love to thank for making this happen today, and also doing many things which were innovative and which may not have happened this year, but which we will definitely continue to innovate on in the future. Next slide. And in particular, I wanted to single out Vincent Levesque, who's done just a tremendous amount working with the IEEE transactions on haptics, setting up the program, and in many other roles, as well as Veronica Santos, serving as publications chair, and also as the editor-in-chief, and you'll hear from her a little bit later. Next slide. There's many other people, and we could spend a lot of time, and I wish we had the time to thank everyone that's on this list. We really appreciate, and the community really appreciates everything that everyone has done. Next slide. We have a number of sponsors who really have helped make this event possible today. These are a list of those sponsors, and you'll see a slide with them throughout the presentation as well. So thank you all to those sponsors. And we had a number of exhibitors as well. These exhibitors weren't able to present this year, but we are really looking forward to seeing them at the next event that we have upcoming.
And you know, really critical to this year's conference was the conference editorial board. In fact, this was something that Greg and I took the initiative to initiate as an independent editorial board that would vet the scientific content in the conference. They worked really hard on the proceedings for the conference. Veronica Santos was the editor-in-chief. Fernando Bello and Ingvars Bersniks were the other two members of that conference editorial board, and we thank them very much for their work. And I'm going to stop sharing here, and we are going to thank you again for joining for this new format for us. And Greg and I are going to turn it over to Veronica Santos, who will provide a message from the conference editorial board.
Hello, I'm Veronica Santos, and I had the honor of serving as the 2020 IEEE Haptics Symposium Publications Chair, as well as the Editor-in-Chief alongside editors Ingvars Bersniks and Fernando Bello. Conference technical paper submissions, of which there were 73, were evaluated by 3 or more subject matter experts via a single blind review process that was managed by the 23 members of our program committee, the conference editorial board, and our program chair, Vincent Levesque. An exciting new addition for 2020 is the IEEE Transactions on Haptics, or TOH, short papers track, which attracted 86 submissions in its first ever offering. The short papers track enables authors to present their work at a conference while simultaneously publishing their work in journal form. This new endeavor would not have been possible without the strong support and commitment of the IEEE Transactions on Haptics journal. The TOH short papers track was managed by TOH Editor-in-Chief Lynette Jones, TOH Associate Editor-in-Chief Çağatay Başdoğan, TOH Associate Editors, and TOH Guest Editors. The conference editorial board sincerely thanks everyone involved in the editorial process, including the many ad hoc reviewers who served the conference technical paper and TOH short paper tracks. We are delighted to present a total of 41 conference technical papers and 36 TOH short papers through our online video program. We hope you enjoy some of the highlights presented in today's live stream program, which is comprised of works under consideration for a number of awards. We encourage you to stay to the end of the event, when Awards Chair Catherine Kuchenbecker will be announcing the award winners.
Hello, I'm Joshua Brown from Queen Mary University of London, and I'm going to talk to you about a soft haptic device that uses particle jamming to present tactile vibrations. Particle jamming is a physical effect that takes place when small granules of material like seeds or sand are compacted together, creating a stiff structure that is much harder and more viscous than the material in its fluidic state. This controllable stiffness has already been used to create tactile displays based on variable stiffness cells and soft robotic grippers that mold themselves around objects to be manipulated. To explore how this concept could be applied to vibrotactile devices, we created a test setup to use to experiment with different input parameters. This consists of a sealed box with a soft silicone cover, which housed an eccentric rotating mass-type vibrating motor suspended in quinoa seeds. This apparatus was then connected to a control unit, allowing both the power supply to the motor and the negative air pressure inside the box to be altered. We hypothesized that increasing the vacuum pressure and thus jamming the particles together more strongly would restrict the movement of the motor, decreasing the amplitude of vibrations transferred to the tactile pad. As you can see, the device not only uses particle jamming to control vibration, but also hardness and softness and texture intensity, as well as being able to use positive air pressure to change shape. We conducted experiments to characterize the device's response to electropneumatic control, that's independent control of the vacuum pressure in the electrical motor power, and mechanical interactions with the user's fingertip under different amounts of force. These are the key physical relationships that will inform the system model and controller design. A very small MEMS accelerometer was used to record the vibration produced by the device throughout all the experiments. The first result we looked at was the effect of vacuum pressure, and therefore the particle jamming effect, on vibration output. We found that increasing vacuum pressure and stiffening the particles led to a reduction in amplitude, which leveled off at about -10 kilopascals. There was a slight variation in vibration frequency, but this was generally consistent across the full pressure range. We then analysed the effect of motor power. This had an exponential effect on amplitude, but only under low vacuum. Frequency was affected approximately linearly under all pressure levels. The vibrations recorded under fingertip pressure revealed very similar effects to air pressure in terms of frequency, amplitude, and shape. This suggests that the mechanical interaction could be actuating the jamming effect, which can be easily adjusted for in the controller. The result also suggests that there may be mechanical alternatives to heavy and expensive pneumatic systems in the future design of devices based on particle jamming. So where do we go from here? Firstly, a closed-loop controller needs to be implemented. After this, the technology can be integrated into interactive devices such as joysticks, gloves, and VR controllers, and the pneumatic control system will be miniaturized. Psychophysical studies will also be conducted into the effect of particle jamming on surface texture and users' perception of vibration intensity.
Hi, I'm Gregory Reardon from UC Santa Barbara, and I'll be presenting our work Elastowave, localized tactile feedback in a soft haptic interface via focused elastic waves. There's been a growing interest in the haptics community to develop haptic devices using soft materials which can bend, stretch, and conform to a diverse array of objects. In addition, recent research on focusing acoustic waves via an array of actuators has shown we can deliver localized tactile feedback at distances away from the actuators. These developments enable us to position any rigid actuation component away from the soft interface surface and still deliver localized tactile signals. Integrating soft materials and localized haptic feedback by remote actuation can enable the creation of a new generation of soft haptic interfaces and expand the design space in areas ranging from automotive interfaces and game controllers to wearable technologies and expressive computing. To test the feasibility of this idea, we constructed the Elastowave, a soft haptic interface composed of synthetic medical gelatin and an array of 16 piezoelectric actuators. We leverage mechanical transmission in the medium to position the actuator array away from the active space of the interface, allowing it to be greatly deformed, bent, and stretched. Wave focusing is achieved via time reversal methods, which are robust to medium heterogeneity and hold for arbitrary medium geometries and actuator configurations. By measuring Green's functions from each actuator to the focus location and invoking the time reversal invariance of the wave equation, the time reverse versions of those measured impulses are also solutions to the wave equation. Driving each actuator with its time reverse impulse response convolved with an excitation signal yields a focused wave field specified by the equation at the bottom of the screen. At the focus location x0, the term in the brackets becomes the autocorrelation of the impulse response between the actuator and the focus location. This implies that our time reversed impulse responses compose a spatiotemporal matched filter and allow us to maximally focus energy at a remote location at time t. We measured the impulse responses from our 16 actuators to 14 different focus locations using optical vibrometry, and used the same vibrometry method to image the surface of the medium during focusing. Applying the time reversal process produced a set of 16 driving signals for each of the measured foci. Driving our actuators with these signals yielded a wave field that reached spatial maximum at focus location x0 at t equals t0, and then quickly decayed. At the focus, peak displacements range from 30 to 100 micrometers and were composed of broadband energy centered at 200 Hz. For all foci measured, the energy was confined to a region on the surface of the medium with less than 1 centimeter diameter and at the desired location. Some varying focus behavior was observed as we moved away from the actuators and towards the medium boundaries. We were able to focus simultaneously at multiple locations on the medium surface by superposing our focus wave fields through additive combination of the actuator driving signals for different foci. We performed a psychophysical study and found that the produced tactile feedback was localized and perceptible. In a first experiment, 10 subjects were asked whether a stimulus was focused either the left or right index fingers. All subjects had 100% accuracy. In a follow-up experiment, the same 10 subjects were asked whether a stimulus was focused to either the left index, right index, or to both fingers simultaneously. We found that all 3 stimuli could be discriminated between with high accuracy. To conclude, in this work, we demonstrated that we could produce perceptible displacements across a soft interface surface using wave focusing methods. We believe that our approach, because of its generality for different complex media and actuation settings, can enable new interfaces in a number of growing areas and allow interface designers to experiment and create with soft displays. Thank you for your time.
Hi, my name is Tom Xu, and I'm from the University of Virginia. Now picture this. When we are doing the grocery, we need to pick the right fruit from the shelf to eat. So which one should I take? In fact, with respect to compliance, we employ distinct exploration procedures to improve our perception. For instance, we may use the pinch grasp to compare them one by one, or we can use the single finger touch to exert a pressure against a resisting force. So in this work, we are trying to investigate these perceptual strategies that can improve our perception of compliances. The first strategy is based on differencing rule. The 2 observations are subtracted, and the result is compared with a threshold to make sure whether these 2 are the same or different. Here, we use the force-related cues to quantify this differencing rule. For the second strategy, it is based on the independent rule. The 2 observations are recognized individually, and the results are compared with the threshold. If they are both beyond the threshold, we take them as the same. Here, we use the virtual stiffness cue to quantify this independent observation rule. We use different experimental setup to quantify the perceptual strategies on the 2 different exploration procedures of the single finger touch and the thumb index pinch grasp. For the first strategy of differencing rule, we calculate the dissimilarity of force cues between the soft and hard palms. The minimum exploration time is achieved when we have the sufficient differences in force cues. The results indicate that, by employing the differencing rule, the pinch grasp requires lesser time for discrimination. For the second strategy of independent rule, we use a recursive Bayesian model to estimate the virtual stiffness. The minimum exploration time is achieved when we have a reliable estimation of the independent virtual stiffness. The results indicate that, by employing the independent observation rule, the hard palm require lesser time for recognition. In general, by employing the pinch grasp, the temporal cues affords greater efficiency with respect to the exploration time and the discrimination performance. So in general, in this work, we try to investigate the perceptual strategies that can improve our perception of compliances. The minimum exploration time is estimated by each of the strategy, and overall, the natural gesture of pinch grasp affords greater efficiency for discrimination. Thank you.
Tangible objects are used to enhance immersion in virtual environments. However, they are often passive or unable to simulate rich, varied mechanical properties. I'm Steven Villa, and I'm presenting a work which combines simple passive tangible objects and wearable haptics for improving the display of varying stiffness, friction, and shape sensations when using tangible objects in VR. We ran 3 human subject experiments evaluating each one of these properties. In the first one, we evaluated whether it is possible to decrease the perceived stiffness of tangibles by providing timely additional cutaneous pressure. We asked participants to use a wearable cutaneous device on their finger middle phalanx and interact with a tangible piston. We used a device composed of 2 motors and a belt that can apply variable pressure and skin stretch sensations. Starting with a compressed finger, we test if decreasing the applied pressure whenever the user contacts an object can decrease its perceived stiffness. Results suggest that whenever the device was diminishing its pressure, user perceived the piston softer than it really was. This effect only works if the device pre-compresses the user finger for a certain amount of time, limiting how often we can exploit this effect. The second experiment evaluated if, by applying timely cutaneous stimulation, it is possible to create the illusion of touching bumps and holes on a flat surface. We ask users to wear the device and sweep on a screen. We test 2 ways of providing this illusion, either by applying varying pressure or skin stretch when encountering the virtual bump or hole. Results show that both rendering techniques work quite well in simulating the presence of bumps and holes on this flat surface, especially when rendering bumps. The rendering with pressure worked better than the rendering with skin stretch when simulating the presence of holes. Finally, in the third experiment, by applying timely skin stretch simulation, we studied whether it is possible to make a tangible object feel more or less slippery than it really is. We ask users to sweep on the screen while wearing the cutaneous device. Results show a recognition rate above the chance level. However, its performance is lower than the registered on the previous experiment. Finally, we demonstrate these techniques in a VR use case, using the wearable device to alter the perception of stiffness and shape of a tangible object. The user has to palpate the abdomen of a virtual patient and locate a virtual kyst, simulated by a bump, and a tender zone simulated by a softer zone.
Hello, I'm Takahashi from the University of Tsukuba, Japan. Today, I'd like to talk about interpersonal biotactile feedback via waves transmitted through the skin from one person to another. Here, we consider the situation in which 2 people are holding each other's hand and one person's smart bracelet is vibrating. In this study, we first measure mechanical propagation on the skin of the transmitter person using an accelerometer array. Then, we also conducted psychophysical study to measure perceptual magnitude of the receiver person. Finally, we compare the mechanical and the perceptual magnitude to understand the characteristics of interpersonal biotactile transmission. Our motivation is to augment interpersonal touch to facilitate social interactions. So I hope the outbreak of COVID-19 will end soon. We have developed smart bracelets that can measure the touch and provide real-time visual and biotactile feedback. This video demonstrates the interpersonal tactile apparent motion. The pair feels vibration moving from one to another. It uses vibration propagation in the skin of the hands. To design haptic augmentation of interpersonal touch, we need to know human factors of the interpersonal biotactile transmission. Therefore, the purpose of this study is to understand characteristics of interpersonal biotactile transmission. The vibrator was attached to the wrist of the transmitter person. We studied the effect of actuation direction, such as normal and tangential, and vibration frequency, such as 50, 100, and 200 Hz. First, we used an accelerometer array to measure mechanical magnitude. Then, we used a second person's finger and magnitude estimation method to measure perceptual magnitude. The x-axis shows the position of the sensor, and the y-axis shows the mechanical or perceptual magnitude. The tangential actuation and the lower frequency generated strong mechanical propagation. The result of perceptual measurement also shows a similar tendency. We found a high correlation between mechanics and perception. We also studied the effect of mechanical direction of propagation, such as transverse and longitudinal waves on perception. If you are interested, please see our proceeding. Thank you for watching.
We have Taku Hachisu using vibrotactile feedback via waves. And so, since we already have a number of questions from the audience, I want to start with some of those, and we'll hopefully have a few minutes to engage in discussion here. There was a lot of questions about Elastowave, and so we'll start with you, Greg. And one of the questions they have to do with how the material actually works and how far you can stretch its capabilities, including how much can you vary the modulus of the wave medium and still achieve perceptible effects? What is the effect of bending? I think there's a lot of interest in, you did flat.
Hi, Karen, sorry, it seems that there was some problem with the audio and we couldn't hear the beginning. Can we start over with introductions from the authors?
Okay.
Thank you.
So I start by at the point of introducing the authors.
Yes, thank you.
Okay, so I am Karon Maclean from University of British Columbia. I'm chairing the session. And so going through each of the authors, we have Joshua Brown on particle jamming paper, and we have Greg Reardon on Elastowave. We have Zhang Zhu on time-dependent cues. And we have David Stephen Villasalazar on altering the perception of tangible objects using wearable haptics. We have Taku Hachisu on vibrotactile feedback via waves. Okay, and so continuing from there, we've noticed that there's quite a few questions about the Elastowave questions to start with that were oriented at how it works and how far you can take it, and also because you did the studies that you reported on the flat surface, but it's flexible, it's a soft robotics. How does the curvature feed into it? And if you could talk about that for a minute.
Of course. Thank you very much for the question. Great question. So we didn't have much time to explore how much we could vary the properties, but generally, because our method is completely data-driven, you could imagine that you could adjust the modulus very much and still achieve perceptible effects. The selection for us for choosing synthetic medical gelatin was to reduce the impedance mismatch between a human who is a human finger and the device itself. So adjusting the modulus would not change the acoustic focusing, but it might change how much energy is actually delivered to the user's finger. And with respect to bending, so we did not take measurements under various contact conditions or while the device was being stretched, but from our psychophysical studies, it appears that even for relatively large deformations for user input, we were still able to get very robust results, and the method still functioned very well.
Okay, so that's great. So you could wrap this stuff around surfaces and you think it would still work as long as you could deliver the stimulus to the material. Yeah, absolutely. You could easily, if you can wrap it around the surface, as long as you can take measurements while it's wrapped around that surface, there would be no problem. That's great. Let's just kind of going on. So your project was about putting a layer of something on another surface, and then a completely different approach that was taken by another author here was to put something on your body, a wearable thing that would actually modify what you're feeling. And so I wonder, Steven Salazar, if you want to talk a little bit about your project. And there was some questions about I noticed that you felt you had much better results for stiffness and bumps and holes and less for the texture. And I wonder if you could talk a little bit about why that was and where you see that going.
Yeah, exactly. Our project mainly focuses on providing tactile stimulation in the middle finger phalanx and not in the fingertip as some other devices does. And we stimulate via skin stretch and via pressure at this part of the finger. So the cues are very clear when you press the finger. For instance, for rendering a bump over a flat surface. But when it comes to feel friction, to feel a surface that is stickier or slippery than other surface, it's harder to relate this stimulation since the stimuli is not being provided at the fingertip, and we generally recognize the friction based on the receptors at the fingertip. We think that's why the results for friction were lower than the results for bumps and holes, mainly.
Okay, and also an answer to a question that was posted. I think the mechanism is skin stretch, not electrotactile. That was a question from the audience. So there's another great question for Taku, which is, did you collect any qualitative or subjective descriptions of interpersonal vibrotactile feedback? So what was the experience like? And for the users, and I will also kind of ask you to explore, this is for when, I think this is for when people are touching each other. So it's interpersonal touch. And maybe you could talk about why you would want to modify, if people's hands are already touching, why would you want to modify the way that that feels?
Okay, thank you for question. And for the first question, yes, actually we informally collected the subjective feeling of the vibrotactile feedback. And generally lower frequency was easily felt, and higher frequency it's difficult to feel. But yeah, higher frequency kind of induce a tickling sensation. And for the second question, what was that? So I think motivation for the modulating the sensation of the interpersonal touch. Yeah, actually, we are trying to develop the kind of augmented reality system for the interpersonal touch. So yeah, actually, we want to make a kind of entertainment system that use the vibration or visual feedback for the interpersonal touch.
Wonderful, thank you. Okay, oh great, there's a question here for Joshua for the particle jamming. And it says, are there, one very interesting work, are there any interactions between the vibration and particle jamming? For example, does the vibration actually affect the stiffness?
So that's a very good question. Not to any extent that we've been able to observe yet. Theoretically, it's certainly possible that there would be, on a particle-to-particle level, a change in the interaction force between individual granules of the particle fluid. But the experiments we've done haven't been able to verify that empirically yet. But that's something that we could certainly do either in a more detailed experiment or by simulation, in fact.
Okay, can I ask a follow-up on that also, or it's actually a little bit different, but if what you imagine using this device for? And also, so you've found this really unique way of producing a kind of a tactile feedback, but where it's a larger form factor than like some of the vibrotactile actuators that we have now. So where do you see this being useful? What do you plan to use it for?
Yes, so as this is a soft technology, it's very well suited to wearable devices, and I'm thinking about sort of applications in belts, gloves, vests, that kind of thing.
Mm-hmm.
I'm also quite interested in shoes, as there is from the literature a known potential to use vibration to generate a sensation of motion, and we could also employ the softness control to emulate texture under the feet, so terrain differences.
So I think you're saying both that it could be intensely miniaturized over the current version, and also that it has some different qualitative parameters that make it more appropriate for some applications than our current hard actuators.
Definitely, it's very much a multiple input, multiple output sort of control model that you're thinking about. So there are a lot of parameters that you can tune and get as output. Yeah.
Okay, wonderful. Thank you. I think we're catching up on the questions that the audience are asking, so I'm going to jump over to one of my own for Shang. So your paper explored these different perceptual strategies that people actually use when they're trying to discriminate compliance, and you went back to some very old work and then tried to use that to leverage taking computational models and actually figuring it out from there, what's really going on when people do this. And I have a question. How would you know if your modeling approach actually reflects the real strategy that people are taking? I mean, you're getting some outputs. You're kind of making a black box model of how people are doing it and proposing two different strategies. What is the approach you actually take to verify that this is actually what's going on in people's brains when they're doing this?
Yeah, thank you for the question. This is a great question. So in this work, we have the estimation of minimum exploration time for each of the strategies based on the computational model. But these findings are derived from the aggregated results. So if we further want to clarify the utility of the perceptual strategy going in the mind, so we need a trial by trial analysis. So that means we need to determine which strategy was using for that particular trial. So in fact, our ongoing work, which is extension to this technical paper, is addressing this problem. So actually, we are controlling the exploration time trial by trial, and we need to we find out whether there is a adaptation between these two perceptual strategies. So imagine, so if we have limited exploration time, so people might using the differencing rule, which is way more faster. So their force curves diverged at the early point. So we know people are using this differencing rule to finish the discrimination task. But when we have sufficient time for exploration, we might use the recognition rule, the recognition strategy, because we can have the robust estimate of stiffness. So there's kind of adaptation mechanism between these two perceptual strategies with respect to the speed accuracy trade-off for discriminating softness. So it is a work in progress, but we are addressing this problem.
And I hear what you're saying is that it's not one or the other. You suspect it's not one or the other, that people are using both or in combination or at different times.
Yeah.
And that's what you're trying to uncover.
Yes, our preliminary results indicate there is kind of a sweet spot where people are adapting these perceptual strategies.
Mm-hmm. Wonderful. We have another question for, yes, for Pedro, so sorry, for Greg Reardon, to say how few actuators does one need to position a tactile point? Does it depend on the 3D geometry of the malleable sheet? So this is really, again, talking about kind of what is in the extreme, where could you take this idea?
Yeah, great question. So that's actually what's, to me, really cool about this method is that you basically could have an arbitrary geometry and an arbitrary configuration of actuators. So they could line the outside of the 3D geometry, or you could, as we did in our case, place them at one end of the medium, and you can reduce the number of actuators so long as you can provide sufficient energy to excite the medium. That's really the main lower limitation, and you could have as many actuators as you want in order to deliver feedback at points that are very, very far away from the actuator locations. So that's to me one of the coolest things about this is it really is up to you and where your creativity takes you.
And how hard is it to make this material and the actuators, like is it is the internal structure in the elastomer, or is this a very easy construction to make?
So the process takes only a few hours. We just have a mold that we pour the gel, that we heat up the gelatin in, and then it just conforms to the mold. And then you can scrape off the top to make sure it's flat. So we just heat it in a conventional convection oven, and that allowed us to mold it to any arbitrary shape. So, and then it cools overnight, and then the only thing that you need to do in our setting was make sure to, after that cooling process, in order to take vibrometry measurements for us, we needed to dope the top surface with reflective beads. And that allows us to estimate the impulse responses from the actuator to the tactile point or focus location. Alternatively, if you have a set of accelerometers, something like that could be used as well, which wouldn't require you to dope the top surface of the medium.
Okay, fantastic. So it sounds like this is a very accessible technique as well as, and you could adapt it to a lot of different surfaces. There's a request for me to tell the audience that there is a higher resolution 1080p YouTube feed that you can select. So if you're having trouble seeing the video adequately, and this is especially when we go to the next session and you'll want to watch the videos at maximum resolution. Okay, back to the questions. There's a question for Stephen Salazar. It says, which is actually about your methods here that you're used to implement your method using a Novant Falcon, and they were wondering if the position sensing resolution and force output accuracy is sufficient for the objectives you have for this work.
Yeah, actually that was a question we had at the beginning of the project, if how feasible is to develop this using the Falcon device. And we found some works in literature recommending to use only the central domain of the workspace that the Falcon provides. So we focus only on that, and we tried the most to be constrained to that central region to take advantage of the high resolution of the Falcon and have a proper haptic feedback.
Okay, thank you. And I want to make sure I've got all the questions from the audience. There's one more, and then I have a few questions of my own that I wanted to ask. So this one is also for Stephen. What performance result would you actually collect from the abdomen palpation? So I think they're looking, what is the higher end performance that might be available, not just with this version, but where do you anticipate it being able to reach? So it's quite related to the previous question.
Yeah, the point is that we didn't record qualitative data from the use case, as that was an example, but from the qualitative information that the participant gave us, he actually was able to reach the kyst in the virtual patient without any additional information, only the haptic sensations. So that tells us that for this early prototype, it is already working. But I would like also to highlight that this could be applied to flat surface, for instance, for smartphones. That will be a nice use case as well, as this will introduce an additional dimension for interacting with the smartphones and filling buttons and other kind of shapes within the hardware that we already have in our smartphones, just adding this haptic ring to these kind of interactions.
I think one of it was a good question, and one of the things it raises is something as authors and haptics researchers we often encounter is how there's a question about performance of this technology. We could ask the same for all, and it's very hard to know what the metrics for performance are. And so you answered by talking about the qualitative experience, and it's clear that we don't have really excellent metrics to really, there's things you can measure, but are they the right things? Are they things that really capture what the technology can do? And so I guess this is something that we might talk about as a challenge for the haptics community, is coming up with these metrics generally. So let's see, there's a couple new questions here about some details. I wanted to bump up to a little higher level. And one thing I think we really have an opportunity right now, it's a very unusual time in the pandemic, and we're having this session that's remote and we're not in the same place. And I'm sure many of us are wondering how haptics can play a role in this weird situation. My teenage daughter talks about skin hunger, and we can't touch other people. And you guys are working on this technology that could potentially do something here. And I'm wondering if any of you have thought of applications or ways that you might, the thing that you are working on might apply to this remote world that we're living in right now. The really obvious connection to it is Taku, your project about interpersonal touch was obvious to me, because you're talking about actual physical people touching each other. But I wonder, is there some way, if you're even out on the street and you're physically distancing, could you evolve this technique where this sensation could jump across space in some way? Or if I open this up to the group of you, if any of you have ideas about how the pandemic might influence your work. We have 3 minutes left. Sorry, I threw one out there. I opened that up to everyone.
Okay, this question is for all of us.
For all of you, yes.
Okay, I will try to answer this. Currently, I'm working in a app dance trainer to connect people remotely, as dance is one of the most important cultural things for us, like the Latino Americans. So I felt the need of this during this pandemic, as we are not able to meet each other and interact together. So this is an interesting challenge to solve with these haptics devices. Also, not only the force feedback devices, but also wearables that are the ones that we have at home normally. So this is an interesting point.
Anyone else want to?
Yeah, actually, yeah, I want to say something. So in my opinion, so maybe my research cannot be directly applied to the kind of virtual or distancing haptics, but yeah, maybe I hope my research will be helpful for after the end of the pandemic. So now I think it's time to prepare and think about the after Corona's interpersonal touch interactions. Thank you.
Okay.
And do I have 10 seconds to respond?
10 seconds, yeah, and then move on.
Yeah, I mean, it's a great question. I think that all this research surrounding soft interfaces is super important, because I don't think we know enough about the perception associated between individuals and between individuals and soft devices. So I think this kind of research that everyone in this session is doing is really important to learning more, so that we can reproduce those kind of sensations, so we can have a virtual handshake through the computer or something like that. So I think that this points us in good directions.
Great, thank you. That was a great way to close the session. And I would now, the end of this session, and I'm introducing the next session, which you will now see a series of videos, 5 videos for the next session. Thank you very much.
My name is Thomas Howard. I'm a postdoctoral fellow at the CNRS, and I would like to talk to you about our novel solution for increasing the workspace of ultrasound mid-air haptic interfaces. These interfaces are tactile feedback devices that use an array of ultrasonic transducers to focus acoustic energy towards small regions of their workspace, producing localized vibrotactile stimuli when these encounter a user's skin. By rapidly moving these focal points, it's possible to render vibrotactile shapes in 3D, allowing users to feel virtual objects. Because of their design, these arrays can only generate perceptible focal points within an elongated spheroidal region above the array plane. Basically, they feature a reasonably large vertical workspace, but quickly reach their limits in the lateral dimensions. This is often constraining in virtual reality, especially when users move around. There are two approaches for enlarging an array's workspace. The first entails increasing the array size or using multiple arrays. However, larger multiple arrays increase the complexity of the driving electronics, the power draw, and have a large footprint and cost. The second approach is to make arrays mobile to maintain the best possible fit between the array's workspace and a user's hand. There are two prior examples of this second solution. Sand and colleagues mounted a small array onto a VR headset, and Bryce and colleagues used a Baxter robot to translate an array, effectively increasing its lateral workspace. However, wearable arrays are obtrusive and limited by the direction in which the stimuli can be delivered relative to the user, while robotic manipulators introduce a significant added footprint and cost to the system. We followed the second approach, aiming to provide the largest possible increase in workspace without these limitations. To this end, we designed the Puma, a pan and tilt mount for focused ultrasound arrays which is easily adaptable to various array designs. The device is an aluminum and 3D printed bracket holding a support plate for the array and driven by a pair of servo motors allowing respectively 215 degrees of tilt rotation and 180 degrees of pan rotation. Once we calibrate the device position with respect to the virtual environment, the Puma rotates the array to orient it towards a tracked user's hand or interaction region, providing tactile feedback for virtual objects. We ran a user study to compare usable workspaces between a static array and the Puma. Users touched visual targets appearing throughout the virtual environment with their hand, and the array would attempt to generate a tactile stimulus at the target location. We then asked users to report whether they felt a tactile stimulus, and if so, whether it felt weak or strong. Sampling the workspace like this gave us an estimate of the volumes within which stimuli were perceptible at different intensity levels. Results showed that Puma could deliver perceptible stimuli in a volume up to 76 times larger than the static array's workspace. Despite inter-subject variability in tactile perception, the workspace within which all users systematically detected stimuli still increased more than 14-fold. Furthermore, repositioning the array plane parallel to the hand increased the perceived stimulus intensities compared to those delivered at the same locations by a static array. In conclusion, Puma is a simple, versatile, and low-cost device allowing massive gains in usable workspace for focused ultrasound arrays, increasing their suitability for VR interaction. As a final note, if you're interested in using or replicating our work, the Puma hardware designs and software tools are now open source and accessible on our GitLab. Thanks for watching.
Hello, my name is Hector Barreira, and I'm going to present our work, Path Routing Optimization for STM Ultrasound Rendering. Ultrasound haptic devices offer new forms of interaction. Each ultrasound transducer can be controlled independently, and the aggregate pressure waves produce a tactile sensation in midair without holding or wearing a device. However, controlling the transducers directly to produce a desired sensation is challenging. Instead, we can describe a tactile sensation using a small number of focal points. Two common methods work by controlling focal points: amplitude modulation and spatiotemporal modulation. STM provides some advantages over EM, such as larger coverage and intensity. However, commanding the device is harder, as it requires to specify the paths that produce the desired percent. In this work, we studied the problem of rendering interaction with virtual environments using STM. Previous work simplified this problem by displaying the contact locations and ignoring the forces at those contacts. In contrast, we believe that the display can be richer if it considers the force field produced by the interaction. The challenge is, how do we map force fields to STM paths? We introduced ProSTM, the first method to render an arbitrary force field using STM. Given a target pressure field, we optimize a set of focal point loops that produce the best matching pressure distribution. Our method accounts for several perceptual and technical constraints. First, we move focal points at a speed that favors constructive interference in the skin, and in this way we maximize the perceived intensity. Second, we limit the loop length to ensure that the stimulus is perceived as continuous. Third, we assume that during a time window, the stimulus is perceived as persistent. This simplifies the design of our algorithm, as we can rule out the temporal component of STM. With these constraints in mind, we define our algorithm in 2 steps. Given an input target pressure field, we first perform a coarse initialization step, which downscales the input field and produces an initial set of loops. Then, we perform a refinement step that optimizes the path to maximize the intensity and coverage while satisfying the constraints. The resulting paths produce the best matching quasi-static pressure field. We applied our method to the rendering of gaseous media and perform a comparison with our previous method based in AM. We have validated that our new method provides larger and smoother coverage. In particular, we have observed that AM can suffer ambiguities when rendering large stimuli. We carried out a user study, which demonstrates that our new STM method helps to discriminate such cases. If you own a Stratos ultrasound device, we encourage you to try our method. It is available for download on our website. Thank you.
Hello, my name is Ray Si Zhang, and I am a PhD student working with Dr. Jake Abbott at the University of Utah. In this video, I will present our work, Dimensional Reduction for 6D Vibro-Tactile Display. In this work, we consider status-based vibro-tactile display using a position handheld grasp, which is used in haptic display of texture surfaces and contact event. During haptic interactions, our hand can detect high-frequency vibrations in all directions, but cannot distinguish the directions. This suggests that a multidimensional vibro-tactile stimulus displayed at the haptic interaction point is haptically equivalent to some 1D stimulus perceived by our brain via our hand. Many haptic interfaces can provide up to 6D vibro-tactile display, which motivates us to explore the 6 to 1 dimensional reduction. Our ultimate goal is to generate a given vibro-tactile stimulus using minimal actuation. In this study, we first gathered a large human subject dataset using an untethered magnetic haptic interface to determine the detection threshold for 45 distinct multidimensional vibro-tactile stimuli. Inspired by prior works, we characterized the 1D vibro-tactile stimulus intensity using a 1D skin-absorbed power normalized by the detection threshold. Using our dataset, we found a general quadratic weighting function with a 6x6 symmetric weight matrix can accurately predict the 1D normalized stimulus. We estimated the weight matrix using a linear least square regression approach. We simplified the weight matrix, which originally had 21 independent elements. First, based on our prior work in the 2018 Haptics Symposium, we implemented 2 constraints to the diagonal elements, reducing the number of independent elements to 19. Then we eliminated the off-diagonal element with the highest p-value by replacing it with 0 and repeated until all elements had p-value less than 0.1. In the end, we found including just 7 independent parameters in the symmetric weight matrix is sufficient to capture the couplings between forces and torques rendered at the hip for dimensional reduction from 6D to 1D. The numerical values for these 7 independent parameters must be determined for a given status, which is the topic of our future work. Thanks for watching.
Our paper's title is Vibrator Transparency, Reusing Vibro-Tactile Signal Assets for Different Black Box Vibrators Without Redesigning. Effects of vibration for various objectives have been shown, such as simulating material properties or effective computing. In order to obtain the desired effect, it is required to reproduce the vibration as designed. We focused on the vibrator environments. There are cases where vibrator environments are different at design and presentation time. For example, at the presentation time, the vibrator specification is changed from design time. On the other hand, it is shown that the different vibrators have different frequency characteristics. Then we find the problem. That is, vibrations are not equal even when the same signal is input. Here, this study referred to the vibrator at design time as a reference vibrator. and vibrator as at the presentation time as the target vibrator. To sum up, with a conventional system, vibration depends on input signals and vibrators. It leads to lower reproducibility when vibrator changes. Thus, we propose a vibrator transparent system. It absorbs the difference in frequency response between reference and target vibrators. Therefore, the vibration through vibrator transparent system depends only on input signals. It leads to high reproducibility, even when vibrator changes. The vibrator transparent system converts input signals according to frequency characteristics of reference and target vibrators through layered filters. The first layer corresponds to reference vibrator. The convert filter is switched based on reference vibrator configuration. The second layer corresponds to target vibrator. The convert filter is switched based on target vibrator configuration. It conducted an objective evaluation of reproducibility. We compared three conditions: baseline, proposed system, and conventional system. The results show that the proposed system was superior to the conventional system. And we also conducted a subjective evaluation. Subjects compared the reproducibility between the proposed and conventional systems. They judged the vibrations through the proposed system had higher reproducibility. As a summary, in terms of cost and vibration reproducibility, just reuse of signal assets can save cost, but leads to low reproducibility. On the other hand, redesigning of the signal's assets can improve the reproducibility, but spend the cost. Then the proposed system can reproduce the vibration without redesigning it. It contributes to cost cut.
Touch is a critical aspect of interpersonal communication, such as a friendly introduction to a new colleague, expressing love to a family member, or comforting a friend. A major challenge in the field of haptics is how to provide meaningful and realistic sensations that are similar to what is relayed during social touch interactions such as these. With a stronger understanding of the parameters involved in imitating human touch, we can develop wearable haptic devices for mediated social touch or communication between a human and robot. This research, done in collaboration between Stanford University and the University of Southern California, focuses on investigating social haptic illusions for tactile stroking. We focus on creating a stroking sensation on the arm similar to what is often used for calming and comforting touch. This type of touch is difficult to replicate with haptics because it involves lateral movement over a large workspace. Instead of developing a complex mechanical system that would need to move along this entire workspace, we evaluated the use of haptic illusions via two previously developed devices. The first device uses an array of voice coil actuators to apply sequential discrete normal indentation. The second haptic device uses an array of motors to rotate tactors that apply discrete lateral skin slip. Both of these devices create the illusion of a continuous stroking sensation, even though the stimuli are being provided by multiple points of contact, instead of one single contact point that physically moves along the skin. We conducted a user study with 20 participants to compare these two actuation techniques and determine how many contact points are necessary to maintain the illusion. The participants felt stimuli provided by both devices and were asked to rate the continuity and pleasantness of the sensations. For each trial, we randomly varied the number of contact points that were used to apply the stimuli. We found that the motor device was perceived as more continuous than the voice coil device, but that the voice coil device was perceived as more pleasant. We also found that the continuity increased as the number of contact points increased until there were 4 contact points, and then there was no significant difference as the number of contact points increased. The participants' comments in the post-study survey corroborate these results. While participants may have a slight preference for the voice coil device, the motor device is able to create a noticeable continuous stroking sensation similar to human touch. In summary, we found that incorporating lateral motion increases the perceived continuity of the stroking sensation, and that only 4 contact points are needed to effectively create this sensation. These results can help aid haptic designers in the development of future wearable haptic devices that are smaller in size and require less power for unobtrusive, private, and effective social communication.
Hello, everyone. Thanks for joining us to this second session. My name is Manuel Cruz from Immersion Corporation. I'm the chair for this question and answer. And here with me are the authors of the papers, Thomas Howard, that presented pan-tilt ultrasound media haptics, Hector Barreiro from the University of Juan Carlos in Spain, that presented pan routing optimization for STM ultrasound rendering, Rui Zhang from the University of Utah, that presented dimensional reduction for 6 degrees of the Freedom Tactile display, Yusuke Ujitoko from the University of Electrocommunications, Japan, that presented the vibration transparency paper, and Karon Nunes from Stanford University, that presented investigating social haptics illusions for tactile stroking. Once again, welcome everybody. There are already several questions here in our chat stream. I'm going to start with air haptics. Did the authors consider any occlusion in the tracking of the hand?
Yeah, thanks for the question. So as you might have picked up on the video, it's not necessarily very clear. The tracking system we used was attaching a Vive tracker onto the hand of the user. That way, that basically allowed us to track the user's hand position throughout the entire virtual environment and even far away from the Puma itself. So we didn't really have any problems with occlusion in that sense. You could imagine adapting the tracking by setting up tracking which is based on the Puma itself, for example, using a camera such as a leap motion mounted onto the device itself as it rotates, which would, of course, be interesting in the sense that it wouldn't equip the user with any extra equipment, but would introduce some hurdles in the sense that if the user's hand went out of the tracking region, we'd have issues in knowing where our command point is, basically to know where to rotate the array towards. So it's not an issue we face, but it could become one if we were to base the tracking on the Puma itself.
Thank you. We have also another work that relates to the ultrasound feedback modality that discuss a new method to display haptic sensations. In that paper, basically the authors were using a fluid body to be displayed as haptics modality. But my questions for the second paper to Mr. Barreiro is that this type of method can be applied to other modality, other type of objects that have sharp edges or corners that are not necessarily smooth in nature or soft?
Yes, thank you for the question. That's a good question, actually. Yes, our method is actually quite general. As long as you can represent your interaction as some kind of pressure field, then you will be able to render it with our algorithm. Or our method will try to allocate the resources to best represent it. It's true that maybe sharp corners are a problem because our algorithm is actually designed to try to smoothen out the paths that will be rendered, because that's one of the assumptions that we relied on that stem from observation from previous works. The work of William Freer et al., in which has been studied for the rendering of smooth shapes, such as circles.
Thank you for the answers. Let's move to another question from the audience. This is for Ruisi. The object is dimensional reduction. So how you're able to, when you have many actuators and you represent it only with one, so you reduce cost, but what else is it gained with your methodology? What other benefits do you give, not just cost reduction? Can you elaborate on that?
Thanks for the question. The cost efficiency is the most important part, which also motivates us to the study, but it also can be used in the design of haptics. For example, if we are using a kinetic haptic device which don't provide which cannot really provide high frequency vibrations. In this case, we might want to attach a vibrotactile actuator to it. And then what is the best way to attach the actuator to it? And this work can provide, like, for example, if we attach it, if it's a force-driven vibrotactile actuators, we suggest to attach it orthogonal to the status so that it will provide the most vibrotactile feedback. And if it's a torque-driven vibrotactile actuator, then we suggest to attach it along, like about the status.
Thank you very much. So let's move to some other questions from the audience. There is a question for Yusuke. How can you tell if a certain vibrotactile actuator is capable of simulating some other type of actuators?
Oh, okay. Thank you for the interesting question. In our work, we evaluated only for one of the kind of actuators, which is linear resonant actuators. But our method does not care for the types of vibrator. We call it as black box method. So the same mechanism proposed in the paper can be applied to the different types of vibrators. So the evaluation is one of our future work in which we test the reproduction of the vibration among different types of vibrators.
Okay, thank you. There is a question as well for Karon. Can you elaborate on what only 4 contact points are needed to successfully create the sensations, the means? Does that mean that people felt it continuous?
Yeah, great question. So essentially the outcome of the work is that we only need 4 actuators to create this continuous sensation. We can add more, 5, 6, all the way up the arm, but we don't get any significant difference in how the sensation feels. So this is really great for haptic designers and engineers because we can use less actuators, which obviously is more lightweight, cost effective, less power consumption. And so it really is a kind of a novel understanding that we can just have a couple of points create this long continuous sensation.
Thank you. And so during this session, we have seen that there are multiple modalities of haptic feedback, anything from air pressure, the lateral skin stimulation, and the indentation and vibration. From your work, you presented, Karon, 2 different modalities. Did you consider also vibration? And if not, why not? Pure vibration,
yeah, so,
I mean.
Yeah, that's another really great question. So in previous work, we coupled vibration with normal indentation. So we provided just normal indentation and then normal indentation and vibration simultaneously. And we actually found that there was no significant difference between those 2 sensations that were provided. So in this case, we just stuck with the normal indentation method. But vibration itself has been shown to create a sensation, something called sensory saltation, which is you can show like movement along the skin by providing vibration, which is where this illusion idea kind of came from and stemmed from. But for us, we're really trying to create these emotional and social type of sensations, and just vibration alone, we hypothesize wouldn't be enough to kind of recreate the type of touches that we use to communicate with one another.
Thank you. There are some great questions here in the chat. There's actually many of them. So let me just go through here and pick up one to continue the conversation on the ultrasound haptics feedback. There is a question that says, does PUMA only provide benefits for complex shapes, or will it improve also perception of primities like rectangular or circles? I think that's related to what we just discussed before.
So PUMA doesn't really pose any restrictions on what you can render with it. So It's definitely beneficial for complex 3D shapes because simply reorienting the array in space can allow you to touch virtual object from multiple sides and therefore basically gain an appreciation for what a 3D shape rendered with focused ultrasound is. But of course, I mean, it doesn't take anything away from what you can basically do with a static focused ultrasound array. So if you wanted to render very simple shapes at various locations in space, then Puma could be used for that. And you could render, yes, lines, rectangles, and so on without any degradation to the sensation.
Okay, thank you. There is also a follow-up questions for Barreiro and the STM methodology using ultrasound haptics. I think the path optimization relying on the subdivision and selection. Does subdivision procedure guarantee the maximal coverage of feedback?
Well, the subdivision process is actually primarily meant to select an initial set of loops that, yeah, try to maximize coverage, but also try to find the limited amount of loops that could be rendered, because there's a technical limitation in how many loops you can actually render at the same time without losing power.
Okay, thank you. There is also a question for Luisi. Are there qualitative or effective consequences of vibration dimensionality reduction in your work?
Thanks for the question. As far as I know, I couldn't detect any consequence or effectiveness for it when we do the vibrotactile deduction, because we have some configurations which only has one vibrotactile feedback, like 1D vibrotactile feedback. We felt the same. In my house, since during the experiment, we are wearing headphones, but in the real vibrotactile rendering, I'm thinking it might have some audio feedback, which human can detect the difference. So that's one thing I think it might cause a difference.
Thank you. And I actually have a question for Yusuke on his paper. In your work, you mainly characterize actuators by themselves without actually positioning them inside haptic devices. How should your methodology would apply to vibrotactile systems or devices when they're actually inside a device, and the dynamics would change the way you're going to do the matching or the mapping of one system to another?
Thank you for the question. In that case, in order to apply a method to that case, we need to measure the frequency characteristic in real time, and calibration the system when users holding the vibrators at the time. So the online calibration is required.
Okay, thank you. There is a question for Kara. Do you have an insight on how the spacing between the motors affects continuous sensations, and how close or far do they need to be?
Yeah, great question. So in some prior work, we evaluated the spacing to a limited extent. So there definitely are still a lot of questions about that. Specifically for applying the discrete lateral skin slip with the motor device. We ran a study where we increased the spacing and got feedback regarding differences in the sensation. And from what we were able to find from the quantitative and qualitative data, people couldn't tell a difference between spacing of 20 millimeters all the way up to 40 millimeters. So actually in that case, we needed to drop down the total number of actuators that we looked at to 4 in order to increase the spacing such that it would fit to stimulate people's forearm. And so in that case, we weren't able to see any difference. And so I think the understanding those the distance parameters might vary based on the contact area that you're actually making with the skin. But it does give us a little bit of an idea that we can really stretch these pretty far apart and still have this illusion exist.
Thank you. We don't have a lot of time left, and there are a ton of questions that are very interesting. However, I want to follow the leadership of Professor Maclean and ask you exactly the same question and get your comments on how do you think you can apply your, for some of you might be more obvious than for others, but how can you apply the technologies that you're developing currently to situations in which you have a remote connection, a remote communication, and you lack this physical contact among the persons that are talking? It's open to any of you to answer.
Yeah, I can take this one. So in the case of the device we developed, I don't really see particularly an application in really remote connection. However, when we envisaged the Puma, the fact that we're largely increasing the workspace of mid-air ultrasound haptic interface, we also imagined that it could be beneficial for collaborative works with haptic feedback. And given the fact that the whole mid-air haptics systems are based on this being totally contactless, I imagine that these kind of technologies can be interesting in situations where, well, direct touch and collaborations with a haptic component become complex, as is the case currently.
Okay.
Okay, and if there's time, I would just like to jump in and say that is this idea of long distance virtual communication is the end goal, I would say, for this work on more effective haptics. I would really love to see one day we have some type of clothing where we have these actuators kind of embedded and we can sort of get these emotional sensations. I always think of it as like my family lives on the East Coast in the US and I currently go to school in California, and it'd be really cool if the same way that we send like emojis or like something, if we could send a haptic emoji and it could be felt and kind of expressed. And I think, yeah, like a lot of the things that we're working on in this space, we're not quite there yet, but we're all working together to kind of get to that point.
Okay, thank you, everybody. This concludes our second session for question and answer, and now we are moving into the third session where speakers are going to present their work. Thank you very much.
When we dance with a partner, receive a package from a delivery person, or help a friend move a piece of furniture, we coordinate action with another person. These cooperative tasks are often achieved without any verbal communication, relying solely on visual and haptic cues. In this work, we ask how partners might use these nonverbal cues to delegate specialized roles. We implement a genetic algorithm to create a population of dyads capable of performing a simulated cooperative task. We then explore the genomes of the most successful dyads to see what makes for good cooperation. In our model task, partners sit across from each other and push on an object, an egg. Their goal is to push the egg along a prescribed path without crushing or dropping the egg. Because the normal force on the egg is equal to the minimum of the two agents' forces, at any given time, only one agent affects whether the egg stays intact. Agents are imbued with two separate force controllers, one to track the reference trajectory and one to stabilize the normal force, corresponding to roles T and S, respectively. For each agent in the dyad, we evolve two switching policies based on the haptic and visual cues that determine when that agent changes their role from S to T and vice versa. After evolving thousands of successful dyads, we observed a few common traits in the population. The best performing dyads exhibit remarkable temporal coordination. Agents generally assume opposite roles and swap roles at nearly the same time. we define anti-synchrony as the fraction of time that agents assume opposite roles. If we look at the distribution comparing performance and anti-synchrony, we see that at the leading edge, better performance requires greater anti-synchrony. But what makes dyads coordinate well? We inspect their genomes in search of a pattern. Each dyad comprises 2 agents, and each agent has 2 switching policies. We compare the policies of the 2 agents by calculating a symmetry coefficient for the policy vectors. Symmetric policies make the same decisions given the same inputs. Anti-symmetric policies make the same decision given opposite inputs, like partners sitting opposite each other would perceive. If we compare policies from a random sampling of the population, we get these distributions. But if we look at only the top decile of most anti-synchronous dyads, a pattern emerges. Complementary policies between agents are more anti-symmetric. Our genetic algorithm has evolved dyads that use this asymmetry to arrive at temporal coordination. Good partners complement each other.
Hi, I am Tommaso Lisini from the University of Siena. I am glad to be here to virtually present this work entitled Hand Guidance using Grasping Metaphor and Wearable Haptics. This work proposes the idea of suggesting hand orientation combining vibrations and an easy-to-learn approach. A virtual object and a virtual static wrench are used to orient the hand. Indeed, the subject is trained to align the perceived wrench along with the gravity. As you may see in the video, a user is rotating the hand exploiting vibrating timbals. The goal and the actual orientation are reported on the plot with blue and green arrow respectively, while on the right side is the participant using the system. We exploited a tiny and highly wearable haptic timbals, like this one. Each timbal is composed of a vibromotor enclosed on a 3D printed support. The advantage of wearing a so small device is that we do not have problem in training the hand with camera-based or similar approaches. To guide the orientation of the hand, the system takes advantage of a virtual wrench. So, given the hand with an arbitrary fingertips configuration, like this one, a software collects data from a tracking system and estimates the contact point. The algorithm computes a virtual sphere fitting 3 points, the 3 fingertips. We know that it's always possible to find a sphere matching this point. Then, giving the desired new hand orientation, a virtual wrench is generated and applied to the virtual object. As soon as the wrench is placed, mathematical computation, based on the grasping theory, is performed to generate the haptic cues. The timbals vibrate in accordance with the wrench direction, thus the user has to align the perceived wrench along with the gravity. We tested 2 different policies for the feedback generation. The former generates vibration with an intensity proportional to the norm of the contact forces, while the second approach generates vibration with an intensity depending only on the normal component of the contact force. Additionally, we tested 2 different modalities to inform the user about the reaching of the desired orientation. In the first one, the vibrations were maintained constant until the goal orientation is reached. Differently, the second approach modulates the intensity proportionally to the orientation error. Participants tested all the feedback modalities combinations that are listed on the slide. So they tested the norm of the contact force with constant and variable intensity, and the normal of the contact forces with constant and variable intensity. Results and user experience show that to give information about the actual orientation is crucial to accomplish the task in minor time. Besides the quantitative results, users' opinion pointed out an evident preference for this policy. Thanks for listening.
Hello everyone, I'm Gemma Bettelani and my work is on the investigation of the role of lateral force in texture-induced motion bias during reaching tasks. The research question of this study is based on the results of our previous work, where we showed that touch is an auxiliary proprioceptive cue to guide hand movements. In particular, we demonstrated that when participants slide their fingertip on a rigid plate to move toward the target without any visual feedback on hand location, the tactile motion estimates were biased by rigid orientation perpendicularly and were integrated with the unbiased motor command and the musculoskeletal proprioceptive cues. This integrated estimate resulted into a perceived motion direction that was deviated from the target one. This triggers a correction of the movement in the opposite direction. Here, an example of the execution of the task performed by a participant. The goal of this work is to show to which extent this observed behavior depends also on the lateral component of the reaction force that arises during the dynamic interaction between the fingerpad and the surface of the ridge. Indeed, during slip motions on a lubricated rigid plate, part of the fingertip pushes against the vertical side of the ridges, and this generates, in absence of friction, a reaction force perpendicular to the longitudinal axis of the ridges. When the ridges are oriented, the reaction force can be decomposed in two forces, Fx and the lateral force Fy. To pursue our goal, we developed an experimental setup which consisted of a lubricated rigid plate, whose orientation with respect to the frontal plane of the participant can be varied controlling a DC motor. A leap motion device was used for the tracking of the participant index position. With the 6-axis force torque sensor under the plate, we accurately measured the lateral force. Participant had to move the index finger toward the target direction, sliding on a lubricated rigid plate. They wore an head-mounted display which visualized the target without information on actual end location and plate characteristics. The participant had to perform two different blocks of the experiment, performing two different levels of the normal force. Indeed, modulating the normal force, we can also modulate the lateral force. The experiment was performed for different ridge orientations. Results related to lateral force show that the lateral force is a function of the orientation of the ridges only in the case of the high threshold. Instead, at the low threshold, ridges do not produce a relevant strain of the pulp and the lateral force is negligible. Results related to hand displacement show that the angular deviation of the end trajectory is function of the orientation of the ridges in both threshold conditions. So, in conclusion, in this work we have shown that the lateral force is a function of the ridge orientation only for the high threshold. The effect of the ridge orientation on end motion was found to be larger for the high threshold compared to the low threshold. However, also in this latter case, we still observed the same bias trajectory reported in our previous work, despite the negligible value of the lateral force. This supports our hypothesis that the motor bias arises for the integration of tactile motion estimates and the other proprioceptive cues. Thank you.
Hi everyone, my name is Rahaf Rahal and I'll be presenting our work caring about the human operator, haptic shared control for enhanced user comfort and robotic telemanipulation. Let's start with the motivation behind our work. Haptic shared control for teleoperation scenarios has been used a lot in the literature. It basically aims to share the control of the system between the user and the robot. It has been used, for example, to guide the user towards a desired position or trajectory or away from undesired regions. However, none of these works focus on the user's comfort during teleoperation, even though this is a relevant issue in many applications requiring repetitive or long tasks. A few works exist on the topic in human-robot interaction, but not in teleoperation scenarios. Our main contribution in this paper is thus to present a haptic shared control method that minimizes the user workload during robotic teleoperation. We start by devising a new online metric that is based on the rule estimation, commonly used in ergonomics to estimate the human upper body's effort. Using this metric and an inverse kinematics implementation of the human arm, we can estimate the user workload online. This workload is combined with the information we have about the task at hand to generate haptic active constraints that will guide the user to accomplish the task while minimizing the physical workload required. To calculate in real time the workload value, we assume that the user shoulder is fixed and that the wrist position is known from the pose of the master device. Using inverse kinematics and without any external sensor, we calculate the arm angles, and the workload value W is basically the deviation from the resting pose of the arm. You can see in the pictures to the left, for example, a comfortable pose, and to the right, a less comfortable one with a higher value of W. Once we have this value, we can calculate at each instant the haptic feedback value, which is designed as the weighted sum of two terms, Fw minimizing the workload, and Fr minimizing a task-related cost function. This second term could be anything. It basically represents the task at hand. In our paper, we chose as a representative cost function the distance to the target in a pick-and-place task. The weights alpha and beta are of course designed and they depend on the application. To illustrate our algorithm, we show how the system behaves in a simple task of moving the robot from a point A to a point B with the same height. An alpha of 0 results in a straight line since it's the best way to minimize the distance between the 2 points. As alpha increases, the user is guided along a more curved path to improve the user comfort while teleoperating the robot. We performed the user study with 15 participants to test our system. The task consisted of moving the robot to perform a pick-and-place task on different objects and with different alpha weights. The results showed that an increase in the weight of the human-related component in the haptic feedback improved the user comfort by 30% as measured by the NASA TLX test results, at the expense of a slight decrease in the performance. As a summary, in this paper, we presented a haptic shared control method that accounts for the user comfort in robotic telemanipulation. We provide force feedback to the user that considers both human-centered and task-centered cost functions. More details are of course presented in the paper and in the video. Thank you for listening.
Hello everyone, this is Patrick Dills from the Reach Lab at the University of Wisconsin-Madison. And in this talk, we're going to focus on some recent work where we explored the use of hybrid actuation in kinesthetic handheld haptic interfaces. So the ideal handheld haptic actuator would address all the components of dynamic range, including force, magnitude, bandwidth, and transparency, while being compact and lightweight. Conventional haptic actuators, which are summarized in the table above, have been shown to address only a subset of dynamic range, and they fall short from the ideal actuator. Hybrid actuators, defined in this context as the combination of active energy supplying actuators, like a DC motor, and passive energy absorbing actuators, like a particle brake, have the potential to improve handheld haptic devices. Hybrid actuators have been used in grounding kinesthetic haptic devices, and they've been shown to increase the stable range of impedances, the actuator torque density, the force rendering capability, and the energy efficiency of the actuators. So one might ask why hybrid actuators are not more widely used. And why haven't they been used in handheld and mobile devices? And really the answer is they're complicated. Hybrid actuators sometimes employ mechanical solutions with multiple brakes, clutches, and differentials to make control easier and to mitigate passive actuator nonlinearities. Current control solutions for hybrid actuators often avoid hard nonlinearities in passive actuators by eliminating zero velocity torque, resulting in reduced dynamic range and actuator capability. Our research is focused on a control approach which compensates for passive actuator nonlinear effects while achieving a higher dynamic range. The control approach allows for a simple parallel connection between active and passive actuators. Our control approach uses passive actuator torque feedback and a new torque partitioning method, allowing the active and passive actuators to work together more closely. Torque partitioning uses two methods, which we're calling model-based passive partitioning and stiffness-based passive partitioning. Model-based passive partitioning relies on a particle brake model, which predicts brake torque output, and allows us to remove undesirable brake commands, which oppose the torque command. Stiffness-based passive partitioning controls the output of the passive actuator, and transitions the entire actuator between active-only rendering at low stiffness and hybrid rendering at high stiffness, ensuring the virtual stiffness is rendered accurately. And we experimentally showed that our hybrid actuator and control system can achieve a virtual stiffness of as much as 60 newtons per millimeter at the output, double that of the active actuator alone. Impedance frequency responses show that the hybrid actuator can render a wide range of stiffness over a wide frequency range as high as 100 Hz. And you can really feel the difference when rendering common virtual environments like this button force profile, which includes a high frequency click along with regions of transparency, low stiffness, and high stiffness. We think that with hybrid actuation, it's possible to reach a new level of performance in handheld haptics, where each component of dynamic range is addressed.
All right, well, we'll welcome everybody to this discussions session for the third session. My name is Ed Colgate. I'm from Northwestern University. I'm here with the authors who include Saber Shebani from Indiana University, Tommaso Baldi from University of Siena, Gemma Bettelani from University of Pisa, Rahaf Rahal from University of Rennes, Hills from University of Wisconsin. So thank you all for being here, and of course the questions are now flooding in from the live audience. So let me jump right into some of those. I'm going to start with Gemma. One of the early questions we had is that this is the tactile retargeting work, sort of combining the tactile and kinesthetic cues And the question was, were the trajectories consistent? It may take a little interpretation, but what can you tell us about that aspect?
Yeah, thank you for the question. That's a very interesting question. And I think that the trajectories are consistent because every subject that performed the task have the illusion. So I think that it's also a robust illusion because yeah, all the subjects have the illusion. Some subjects goes more in the opposite direction of the tactile flow, and the other goes less in the opposite direction, but the illusion still remains. So I think it's a robust illusion.
Can I follow up and ask a question of my own, which is, I'm wondering if you could say a bit more about how the tactile part of the feedback registers on the scan. What is the tactile information that your subjects are really paying attention to? Is it the deformation of their skin, or is it the way that they're feeling the ridges as they move?
I think that thank you. I think that the deformation of the skin is very important because as we have seen from the slide and the video, when there is more deformation of the pulp, we have more lateral force, but this lateral force cannot influence the effect of the tactile flow. So I think that yeah, the deformation in this case is not so important.
Okay, thank you. That's very helpful. Let me turn now to Tommaso. We had a question come in from the internet, which is there a special reason for choosing 3 fingers instead of more or fewer?
No, there is not special reason to use 3 fingers. In our experimental campaign, we tested both 2, 3, and 4 fingertips configuration of our system, and we discovered that using 3 fingers is the best compromise between having a precise alignment of the hand orientation with the desired orientation, and complexity from the user point of view, from user side, in following the cues, because wearing too much tactile display on the finger palms can cause some issue in distinguish which is the right cues to follow from the user point of view.
All right, thank you. That's really helpful. And I wanted to follow up on that as well. As I thought about the work, I had a little bit of difficulty sort of visualizing. This is where I really wish we had the demo session. But I had difficulty visualizing what the user experience would be like. And so I wonder if you can sort of give me a bit of a feel, if you will, for the experience of having these different sensations, and then how that compares to the task at hand, which was to sort of orient an object with gravity.
Okay, well, thank you for the interesting question. I totally agree with you that it's not so easy to understand the principle behind our method without testing it. So the idea is to, wearing this small device, you can wear it 1 per finger, and then put the hand in an arbitrary configuration like this one. The software imagine a virtual object and design a virtual object, a sphere, fitting these 3 points. So since the object is virtual, he has not weight, so it's like a gravity compensated object. Then we apply an external wrench to the object, and you perceive through the vibrotactile displays a sort of wrench. So we mapped a wrench into vibrations. Is the easiest way in future work we plan to use display with force feedback instead of vibrations. But vibration is the most simple from a user point of view. So we display this wrench with vibration, and the user is asked to align the perceived wrench along with the gravity. So it's an immediate concept because there is no need to train the user, because a user knows what the gravity is and knows what a wrench is. So the only thing that the user has to do is to align the perceived wrench along with the gravity. And the position of the fingers is not important, since the virtual object is computed by an external software that exploit any
type of cameras, a Kinect, a lip motion, or a bicon tracking system to reconstruct the hand pose. So the idea is this one, is to use the most simple approach to suggest a novel orientation to the users.
All right, thank you very much. Now, let's sort of keep with this theme of asking you folks questions about the experience of users. So Patrick, we have a question coming in about how the inclusion of the magnetic brake impacts the user experience. I wonder if you can tell us a little bit more about that.
Well, I would say that the dynamic range of the actuator, so like the bandwidth of the actuator, forces that the actuator can produce, and the maximum stiffness, they all enhance the user's experience. I guess I'm still a little bit ambiguous about what they mean by the user's experience.
There are actually some follow-up questions. So one of them is, how does this hybrid approach do at rendering virtual environments beyond just stiffness?
Okay, so we definitely focused on just stiffnesses in this work, but I think I can say fairly confidently that it should excel at rendering things like damping, because we have a natural damping source in this actuator. And I don't know if I really should extend much past that. But yeah, it certainly can excel at other impedances besides a stiffness.
Okay, all right. Well, thanks. That's helpful. And let me now go on to Rahaf, and it's a similar type of thing. You're providing kind of as I understand it, sort of virtual constraint to enhance comfort. And so we've got a question. What's the process? Looks like we have. What's your process for determining sort of the optimal, I think it was alpha value in the work, balance text execution with the comfort?
Yeah, excuse me. Can you repeat the question? Sorry.
Oh, did you hear the question?
Can you repeat the question, please?
Sorry. So I think we're getting, other authors could mute for just a moment. I think we're getting a bit of interference. So Rahaf, the question was about how do you choose the optimal alpha to balance comfort and task execution?
I'm very sorry, I cannot hear you. Just 1 second.
Okay. While you're getting that sorted, let me go on to Saber. So Rahaf will come back to you. Saber, I want to ask a question of my own, which is I found the work completely fascinating, this sort of evolving the dyadic strategies. And I thought about a lot sort of dyadic performance between real people. And one of the things that we people have to do is we do joint tasks with whoever happens to be around us. So I'm kind of curious in that spirit, if you were to evolve sets of dyads, find successful ones, and then switch partners, how does that impact performance? Have you looked at that?
That's actually a very great question that we also thought about. After submitting the paper, we went on and analyzed the dyads that we've evolved, and we learned that when we match the different, when we match agents from different dyads, the performance can be poor in some cases and good in other cases. It seems like there's this idea of a universal cooperator or a lazy partner. So if you, for example, have two lazy partners working together, they're not going to do a good job in the task, right?
Right.
But the important thing for moving into humans is that if something that might not translate from the simulation to humans might be that the humans also happen to adapt to each other. So if you put two lazy human partners together, one of them might actually end up picking the load. Right?
Yeah. All right. Thank you. All right. Let's see now if we can kind of get back to Rahaf. Are you able to hear me, Rahaf?
Yeah, now I can hear you. Can you hear me well as well?
Yeah.
Okay,
So a question I had asked from the audience was, how do you select that optimal alpha to balance execution and comfort?
Okay, so actually the alpha parameter depends mainly on the task. For example, if you have a task which requires a lot of attention to the user comfort, for example, a task which is repetitive or takes a long time, then we need to increase this value of alpha. But of course, we need to increase it while taking into consideration that the user should still be able to perform the task. So we cannot increase it to more than 50% of the weight. So of course, it depends on the task, and we test it for different alpha values, so 0, 0.2, 0.4, to be able to see the trade-off and to see also the user reaction about this haptic feedback value.
So building on that point of user reaction, we have a question, which is, did your users have a particular emotional reaction to the guidance, and positive or negative?
Actually, yeah. So usually we always have this problem with user studies and testing their reaction to the haptic feedback that we give them. So in general, users are reluctant to giving control away. So when we guide them towards a specific task, they usually find it hard to follow. But in this case, actually, they preferred the guidance with the user comfort because they felt that it's more easy to do, and it was not as sharp as just following the target. So incorporating the component of the human comfort actually helped the users. They felt that it was more smooth to perform the action.
Okay, terrific. I'm gonna switch back for a moment to Patrick. We have a question, which is, someone said, love this discussion of the ideal haptic handheld actuator. What else do you think is missing? What would make it perfect?
Yeah, I think a lot of us consider what is the ideal actuator in haptics, and I really kind of I mean, I like hybrid actuators, obviously, but I think incorporating like some like multimodal feedback would be interesting, and I think that really with my experiences at going to some of these conferences has like is a mechanism to enhance like an actuator. So like maybe having like a vibrator like in the fingertip of this actuator and incorporating that into like the existing control system that I've developed could be interesting, and maybe would make it a more ideal actuator. Yeah,
that is a tough question, but yeah, I think that's an interesting direction, right? It's sort of hybridizing even further, right? So you've got your brake and your motor, and perhaps sort of a high frequency actuator as well, right?
Yeah.
Interesting. Okay. So let's see. I'm going to ask a question now of Tommaso, and it's sort of the other direction. And it's, and what you're doing is you sort of, maybe force feedback would have been ideal for this task, but in order to make it very wearable and portable, you've chosen to do vibrotactile. Could you go even further and remove the vibration actuators from the fingertips altogether and apply them to some other part of the body? Why did you choose to mount them on the fingertips?
Okay, so thank you for the question. It's really interesting. The point is that there are a lot of technique of strategies that are able to suggest hand orientation exploiting different body parts. For instance, I can easily suggest positioning of the hand using an armband or a vibro bracelet, but it's really difficult to suggest hand orientation using vibrotactile feedback or haptic feedback placed in a different part of the body. This is due to the fact that there is the wrist in the middle, so I can easily suggest the positioning of the hand, but I cannot directly suggest orientation of the hand because I need a sort of translation, I need a sort of mapping between signals in different parts of the body and hand motion to orient, to reach the final orientation of the hand. In this way, in putting the vibration, the haptic displays directly on the hand, we remove this part. There is nothing in the middle, there is not a translator, there is not a mapping, it is just a one-to-one mapping. So I feel a vibration in this fingertip, for instance, in the fingertip of the index, I have to rotate the hand in this way. So also from a cognitive load point of view is more light, our approach. This is why we decided to put displays directly on the finger palms.
Okay. Thank you. Well, we have just a couple minutes left, and I'm not going to be able to get to all the wonderful questions that are coming in on the stream, but I'm noticing that a number of them have to do with application. So perhaps we could close by each of you just saying very briefly what you see as a really exciting future application of the work that you're doing. And Gemma, perhaps we could start with you.
Yeah, so an application for my work could be an haptic targeting application, because in our previous work we have applied a Kalman filter model that explained the trajectories of the participants. So we can apply this Kalman filter to guide the end on the plate and guide the end on the participant toward a target in the framework of the haptic retargeting.
Okay, thank you. Saber?
Yes.
Do you have any thoughts on application?
The applications of my work would be in mostly physical human-robot interaction. So there's this idea of intuitive collaborator, and we would want to see humans become good collaborators in a lifetime of experiencing interactions with objects and with each other, right? So it would be great to be able to demystify what is it in the human intuition that makes humans easily adapt to each other and collaborate with each other. So that would make for an intuitive physical human-robot interaction.
Thank you. Thank you. Unfortunately, it looks like I haven't really timed this very well. It looks like we are essentially out of time. So I'm going to ask the other three authors to maybe give some thought to that question. And I know there'll be a mechanism for providing feedback since there were so many leftover questions. But for now, I want to thank you all for your really great work and participating in this session, and let the audience know that we're going to be moving into the next session, which will be, I believe, the work in progress papers. So thank you all.
Hi, I'm Heather Culbertson, and I had the pleasure of serving as the 2020 IEEE Haptics Symposium Work in Progress Chair. Work in Progress papers enable authors to share late-breaking results with the research community. The emphasis of these Work in Progress papers is on the novelty of the work, not completeness. We received 47 Work in Progress submissions this year. These submissions were evaluated by 2 subject matter experts from the Work in Progress editorial board in a single blind review process. They were evaluated on the basis of originality, relevance, technical soundness, thoroughness, and clarity. We are delighted to present a total of 44 Work in Progress papers in our online proceedings. We hope you enjoy some of the highlights presented in today's live stream program, including the works under consideration for the most exciting Work in Progress paper award. Encourage you to stay to the end of the event when awards chair Catherine Kuchenbecker will be announcing the award winners.
Hello, my name is Melissa Bryan. Our goal in this work in progress is to predict the behavior of a soft bellow actuator for wearable haptic devices. Our approach uses an assumed actuator geometry to relate displacement to volume. We assume that as the actuator inflates, dB and DO stay constant to create chambers that can be modeled as sphere segments with radius r that changes as the actuator inflates. This assumption imposes a geometric relationship between the heights and diameters, leading to an equation that relates total volume to overall height. Using water displacement to measure volume, our test results show that the model is competent enough to predict the trends and approximate magnitude of volume. By assuming no energy loss, a fluid Jacobian was derived to predict the generated force. However, our data shows that energy transformation is not the only aspect of the generated force, and we are currently exploring energy storage as the additional factor.
Sensing friction is important for dexterous manipulation. To measure friction, some subtle sliding or localized slip is required. The question is how to slip safely without losing contact. and the answer to this question is small rotational movement generating torque when we just lift the object. In order to investigate how torques are encoded by afferents, we recorded from single tactile afferent in humans by applying torque in two different frictional conditions, and from the recordings we can clearly see friction dependent response in low and high friction condition. However, SA2 afferents could be exceptionally well suited to signal torque, as their response is inhibited or excited depending on torque direction and scaled by torque magnitude.
Many people who experience dual sensory loss of vision and hearing depend on touch for communication, where unique tapping or sliding gestures on the skin convey meaning. However, interpreters trained in fingerspelling are limited in number and frequently experience physiological constraints, which may lead to social isolation for those who rely on tactile communication. To understand the mechanical profiles of touch gestures on the skin, we used a wearable vibrometry system with 42 accelerometers each on the front and back of the hand to capture the signing of 10 letters of a fingerspelling alphabet. We also used a KL divergence metric to show high consistency between trials of the same letter and clear differences between the letters. Future work involves using feature extraction to identify letters from mechanical signals, informing the design of tactile communication devices.
Hello, and welcome to the awards ceremony for the 2020 IEEE Haptics Symposium. I'm Catherine Kuchenbecker, and I'm the awards chair for this conference. Today, I'm going to be telling you about the awards that we're bestowing on these 5 different categories of contributions to the conference. For each one, I'll be walking you through the process that we went through in order to select the winners and any honorable mentions. Any papers that I personally co-authored were not considered for any of the prizes. In contrast, though, we did consider contributions co-authored by former members of my team, like my previous PhD students and postdocs. I just declared these potential conflicts of interest to the other members of the committee and refrained from evaluating those submissions very much. We also did consider the contributions by the 2 co-chairs of the IEEE Haptics Symposium this year, Greg Gerling and Jan Visell, and we did that because they were in charge of planning the event, but they weren't at all involved in the scientific review process or nominating or reviewing. So we reviewed their papers because they were co-authors just like anybody else, except for me. And lastly, I asked all the committee members who helped me in the award selection process to make sure that they didn't have any potential conflicts of interest in the contributions that they were being asked to evaluate. The first prize is our most exciting work in progress paper. The award committee consisted of Heather Culbertson from the University of Southern California. She was our work in progress chair. Myself, I'm a director at the Max Planck Institute for Intelligent Systems. Masashi Nakatani from Keio University, and Myrtha Plazia from Eindhoven University of Technology in the Netherlands. The process that we went through started with the 44 work in progress papers that were accepted to the conference. Heather went through these and chose 4 finalists that really stood out in terms of the quality of the reviews that they received. The award committee read all 4 of these 2-page papers and decided on our selection criteria. We then chose 1 winner and 1 honorable mention. The 4 finalists were the 4 work-in-progress papers that were presented here in the live stream through 45-second long videos. And the winner that we selected was Modeling of Soft Bellows Actuators by Emma Treadway, Melissa Bry, and Brent Gillespie. These authors will be receiving a $250 prize sponsored by Intuitive Surgical. So let's congratulate them on this great accomplishment. If you haven't read their paper, you should take a look at it. It's available in the proceedings. They go through how to model these little soft actuators with some nice measurements and theory and also open questions. We also selected 1 honorable mention, and that was Tactile Fingerspelling Letter Identification Using Whole Hand Mechanical Signals by Stajara Dinilescu, Gregory Reardon, Sven Top, and Jan Visell. They will be receiving $100 prize sponsored by Intuitive Surgical. Congratulations. Next, we come to the category of outstanding reviewers. Now, these are people who helped review the technical paper submissions. We're not looking at the reviewers from the IEEE Transactions on Haptics papers because the journal has its own yearly outstanding reviewer awards that all those reviewers will be automatically considered for. The award committee was small. It was just Veronica Santos and myself. Veronica's at UCLA, she's our editor-in-chief and our publications chair. So the process that we went through, we had 204 reviewers. Thank you all for contributing to the technical paper track of our conference. Veronica invited all members of the program committee to nominate their top reviewers for this prize. She received 3 nominations, and then she and I went through all the reviews that those 3 individuals submitted and realized they were all awesome, and so we decided all 3 deserve recognition here. And so our commendations for outstanding reviewers of technical papers go to Pascal Fortin from McGill University, Alistair Lutit from University of New South Wales, and Tatiana Sezova-Kajic from the University of Sydney. Congratulations, they each received $100. Now we get to our 2 best paper prizes. First, we're going to be looking at technical papers. The award committee was Veronica and myself, and we were joined by Sunwoo Choi from Posttech in South Korea. He's a former co-chair of Haptics Symposium. The process that we followed, we started with the 41 technical papers that were accepted for publication at the conference. Veronica then looked through all the reviews that were submitted and selected 8 top contenders, our 8 finalists. We met once through video conferencing to agree on our selection criteria, and then we read all 8 of these papers. It was a real pleasure. They were really, really good. And we selected from those, based on our selection criteria, 1 winner, 1 first honorable mention, and 2 second honorable mentions. The finalists have already been shown here in the live stream through their 3-minute videos. Here are the first 4, and here are the second 4 of the 8 finalists for the best technical paper award. The winner, selected unanimously by the committee, was Elastowave, Localized Tactile Feedback in a Soft Haptic Interface via Focused Elastic Waves by Gregory Reardon, Nicholas Kastor, Yitan Shao, and Jan Visell. These authors will be receiving $1,000 sponsored by Facebook Reality Labs. Congratulations. Again, you should take a look at their paper. It is beautiful. They have really nice illustrations explaining how their device functions, explaining the theory behind it, showing measurements, how they made it work as well as it did, and also the results of the human subject study. Our first honorable mention for the best technical paper prize goes to a hybrid active-passive actuation and control approach for kinesthetic handheld haptics by Patrick Dills, Nick Polonaise, Priyanshu Agarwal, and Michael Zinn. These authors receive a prize of $500 that was sponsored by Facebook Reality Labs. So congratulations to these authors for their great accomplishment. Oh no, it was supposed to make a sound. Let's try it again. Oh, there it is. I clicked too fast. You might not know, these 2 authors in the middle, they both work for Facebook Reality Labs. But that didn't affect our decision at all. All right, now we get to our second honorable mention, of which there are 2. The first one goes to time-dependent cues, encode the minimum exploration time in discriminating naturalistic compliances. You had people touching plums. It's by Chang Xu and Gregory Gerling. They received $250 sponsored by Facebook Reality Labs. Congratulations. Our second honorable mention in the best technical paper category is vibrator transparency, reusing vibrotactile signal assets for different black box vibrators without redesigning, co-authored by Yusuke Ujitoko, Shao Sakurai, and Koichi Hirota. These authors also received $250, sponsored by Facebook Reality Labs. Congratulations. Now we get to our other best paper prize, which is for short papers published in the IEEE Transactions on Haptics. The award committee was myself, Vincent Levesque, who's a professor in Montreal, he was our program chair, and then Hiroyuki Shinoda, who's a professor at the University of Tokyo. The process we followed was very similar to that of the best technical paper prize. We had 36 papers from which to select this prize. Lynette Jones, who was the editor-in-chief of the IEEE Transactions on Haptics at the time, selected 6 finalists based on the strength of their reviews. The committee met once to agree on our selection criteria, and then we read all 6 of these papers, the finalists, and agreed on 1 winner, 1 first honorable mention, and 1 second honorable mention. All 6 of the papers were really a pleasure to read. Here are the first 3. They also appeared today here in our live stream event through these 3-minute videos, and here are the second 3. So without further ado, the winner of the Best IEEE Transactions on Haptics Short Paper Award is Path Routing Optimization for STM Ultrasound Rendering by Hector Barrero, Stephen Sinclair, and Miguel Otade. They receive a prize of $1,000, sponsored by Force Dimension. So congratulations to this author team for their beautiful paper. You want to see it? Here it is. They explain a new method, a new algorithm for deciding where to apply ultrasound vibration to create a pressure field across the hand. They have both quantitative results and a human subject study. It's a beautiful paper to read. We had a first honorable mention in the same category, and that goes to Caring About the Human Operator, Haptic Shared Control for Enhanced User Comfort in Robotic Telemanipulation. And the authors are Rahaf Rahal, Giulia Matarese, Marco Gavaccini, Alessio Artoni, Domenico Pratechizzo, Paolo Robuffo Giordano, and Claudio Pacchierotti. They receive a prize of $500, sponsored by Intuitive Surgical. Let's congratulate them on their great accomplishment. And in this category, our second honorable mention goes to altering the stiffness, friction, and shape perception of tangible objects in virtual reality using wearable haptics. The authors are Stephen Villa Salazar, Claudio Pacchierotti, Sergio De Tingue, Anderson Maciel, and Maud Marshall. They receive a prize of $250, also sponsored by Intuitive Surgical. Congratulations. Now we get to our last prize, which is that of Best Video Presentation. This is the first time we've given such an award. We had here a coordination committee because this prize was determined by audience votes. The 2 people who helped me run this prize were Ildar Farkhatdinov from Queen Mary University of London and Claudio Pacchierotti from the University of Rennes, INRIA, CNRS, and IRISA. They were both members of our organizing committee who were already helping with videos and demonstrations and exhibits, and who agreed to help run this prize with me. The process we followed was that we had 77 3-minute-long video presentations, which are all available on our website. Everyone who was associated with the conference in an official way, either by registering, co-authoring a contribution, or participating as a volunteer, was invited to vote for their 5 favorite videos, not counting videos by yourself, other people in your lab, things like that. For the coordination committee, we tallied all the votes, we removed the invalid votes, and then I alone looked at all the vote tally in the end and chose 1 winner and 3 honorable mentions of equal level. The winner of our Best Video Presentation Award is a hybrid active-passive actuation and control approach for kinesthetic handheld haptics. We've seen this author team before, and they win for this prize $500, sponsored by Facebook Reality Labs. Congratulations. It's a beautiful video. Our first of 3 honorable mentions goes to the Elastowave team, which you already heard from. They get here $250, again sponsored by Facebook Reality Labs. Congratulations to the Elastowave team. Our second honorable mention is a paper you haven't heard about yet, and that is Interpersonal Vibrotactile Feedback via Waves Transmitted Through the Skin, Mechanics and Perception by Taku Hachizu, Gregory Reardon, Nicholas Kastor, Etienne Shao, and Jan Visell. They win $250, sponsored by Facebook Reality Labs. Congratulations. And then our third honorable mention goes to Puma Pan-Tilt Ultrasound Mid-Air Haptics for larger interaction workspace in virtual reality. And the authors here are Thomas Howard, Maud Marshall, Anatole Lecoyer, and Claudio Pacchiarotti. They received $250 by Facebook, sponsored by Facebook Reality Labs. Congratulations. So that's it. Those were our 5 awards. Congratulations to all the winners and the honorable mentions. A few small follow-up things. I am really sorry if I said your name incorrectly, if I showed the wrong photo, if that wasn't actually you, I'm really sorry. Or if I made any other errors in my presentation. We'll correct all the information if there were any problems. When we put it up on our website, our webmaster, Oliver Schneider, will be helping me in the coming days get all of this posted up there so everyone can see it. We will also be contacting the winners and those who won honorable mentions to communicate about how you'll be able to receive your certificate and your cash prize. If you haven't heard from us by July 4th, please just send me an email and we'll sort out where things might have gone wrong. With that, I would like to bring this award ceremony to a close by congratulating all the winners, honorable mentions, finalists, authors, and thanking you all for your kind attention.
I'm Domenico Pratichizzo. I am the new editor-in-chief of the IEEE transaction on haptics. It is for me a privilege to be editor-in-chief of such a prestigious journal after the mandate of Lynette Jones and Ed Colgate. Our journal is a very important journal in our community. It's interdisciplinary, it's very attractive, it's collecting most of the more interesting and important work in the field, and we want to keep pushing in this direction. One of the main important role of myself is to build a very strong editorial board. I want to introduce to you my associate editor-in-chief, in particular Marcia O'Malley and Segmon Choi, and the editorial board that now is composed of Hiroyuki Kajimoto, Luca Braida, Jean Park, Christian Olds, Astrid Kappers, Don Giulì, Matteo Bianchi, Lana Nischi, Kyle Reed, Jonathan Salvietti, Ishohiro Tanaka, Eckhard Steinbach, and Jessica Archer O'Brien. This editorial board will work with me to motivate authors, to encourage readers to contribute to the journal by reading it, and also reviewers to contribute to the growth of our community. I'm very proud to announce the latest awards of our transaction haptics, and in particular our Best Paper Awards for 2020, and the Best Paper Award founded by IEEE Robotics and Automation Society is the paper by Charlotte Reed, Hong Tan, Zankar Perez, and Courtney Wilson, and Federico Severnini, Zhong Jun, Juan Martinez, and Yang Zhao, Ali Israf, Francis Lowe, Kate Klumb, Robert Turcott, and Fendi Abnussi on phonemic-based tactile display for speech communication on volume 12, number 1 last year. The second award is the Best Application Paper Award, founded by Alps Electric, and it is a paper published on volume 12, number 4 last year. Jean-Baptiste Souchot, Daniel Chen, Yang Lee Park, and Pieper Schull on a soft wearable skin stretch device for haptic feedback using twist and coiled polymer actuators. So congratulations to these awards. I want to thank all of you to keep this journal growing, and I want also to thank Lynette Jones with her team that had worked a lot in the previous years, in particular in contributing to the new initiative with the Haptic Symposium and Transaction Haptic that we want to keep pushing. Thanks again.
And have a nice day.
Hello, Haptic Symposium. We are very happy to announce that EuroHaptics is still happening in September.
And it will physically take place in Leiden, the Netherlands.
In order to do so, we will strictly follow the COVID restrictions, like social distancing and a maximum number of participants.
That is why we're sending this message especially to the Haptic Symposium community. We still have a limited number of places available. We are very much looking forward to finally meeting you again in real life.
We believe that this will be a very unique and interesting edition of EuroHaptics. So please register as soon as possible.
So, on behalf of all the members of the organizing committee, enjoy the online Haptic Symposium, and we hope to see you all again in Leiden.
Hello everybody, this is Danxiao Wang from Beijing. First of all, I would like to express my deepest thankfulness to the General Chairs and Organization Committee of Haptic Symposium for giving me this opportunity to share some important updates about Asia Haptics 2020. The year 2020 started with a hard mode, especially for international conferences and events. Due to COVID-19, many conferences were cancelled, postponed, or presented via virtual video streaming. After several rounds of serious discussions with Asia Haptics Steering Committee, we are very sorry to announce that Asia Haptics 2020 will be postponed for another 2 years. This means that we will have it in the November 2022. This was a hard decision to make, but for Asia Haptics, which has a unique signature of haptic-oriented demonstrations, with special emphasis on try-on experience, we have to do so. Although the main conference is rescheduled, we plan to organize a special online workshop in November this year. The tentative time for the workshop is November 9, 2020, 8 p.m. to 11 p.m. in Beijing time, which will be 7 to 10 a.m. in Chicago and 1 to 4 p.m. in London. The workshop will be about 3 hours long, with 3 invited keynote speakers. We are very glad to have Professor Edward Colgate from Northwestern University, Professor Eitan Badat from Imperial College London, and Professor Masahiko Inami from the University of Tokyo to deliver the keynote talks. We will also have 3 to 5 selected Student Innovation Challenge teams to present their work using online video demonstration. Virtual lab tours will also be provided by some professors from the Asia Haptics Steering Committee. The detailed agenda of the workshop will be announced later. We sincerely invite you to join this workshop in November, and will be very much grateful if you can advertise it in your social networks. We really hope that this workshop will be able to intrigue more students, researchers, and industrial partners to join the haptics community. We are looking forward to seeing you at the online workshop and also in Asia Haptics 2022 in Beijing. Thank you. Stay safe and healthy.
Hi, my name is Vincent Levesque from ETS Montreal.
And I am Kayvan Hashudizad from Queen's University, Canada. We are the co-chairs of the next World Haptics Conference that will be held in Montreal in July 2021. We have assembled a great team from academia and industry to organize a conference that offers a rich program filled with exciting technical content and also great enjoyment for you and your families. The conference will be held in Hotel Bonaventure right in downtown Montreal near Old Port. The hotel has panoramic view of the city and offers quiet gardens that you will all enjoy.
You'll be coming to Montreal at a great time. You'll be able to see the international fireworks competition on the night of the banquet. And if you arrive a few days early, you'll also be able to see the International Jazz Festival and its many outdoor events. You'll also have a chance to see Montreal's best touristic attractions, including the Botanical Garden, the Olympic Stadium, and some amazing views of the city. You'll be able to visit Montreal's many lively neighborhoods, including the Old Port and downtown. You'll also enjoy great food, such as our famous smoked meat, bagels, poutine, and a vast selection of restaurants for every taste. Here's a short video that highlights what Montreal has to offer.
We look forward to welcoming you in Montreal.
À bientôt.
And yeah, so that concludes our program today. Thank you, everybody.
Thank you very much, everybody, for attending, and for all the organization that went into this event.
I want to give special thanks also to our video production team who helped us to put together this event in short order, and again to all of those who contributed to making this conference happen. I want to give special thanks to our outgoing co-chair, Greg Gerling. You know, Greg, we've had 2 outstanding conferences during your tenure, plus this additional virtual conference that you didn't sign up for, but that kind of makes you the first, I think, IEEE Haptic Symposium General Chair who's overseen 3 conferences, which is pretty great. I don't know if that's true, actually. But I really appreciate your tremendous service. I know the community does as well. This would not have happened without your dedication to, I think, excellence in haptics research, really, and that's reflected in all the exciting new elements that we've added to the conference, and your amazing equanimity in the face of important challenges that face us all in this period. And so, thank you for that. And with that, it's time to announce our incoming new general co-chair of the conference, Veronica Santos of the University of California, Los Angeles. Veronica, would you join us?
Thank you for the introduction, Jan. I would like to take a moment to thank Greg, Jan, and the rest of the organizing committee for their difficult overtime work during this unprecedented year of the symposium. I'm excited and honored to be joining Jan as a general co-chair for the 2022 IEEE Haptics Symposium. And we look forward to producing a high-quality event, and we cannot wait to see you all again in person soon. Back to you, Jan.
All right, and I'm just going to share a few slides because we're already excited about Haptic Symposium 2022, and hope you'll also join us for that conference. The conference will include a whole host of features. We plan to host it at the University of California, Santa Barbara, where I'm based. The conference will include, the usual elements: technical papers, IEEE transactions on haptics, journal short papers, cross-cutting challenge sessions, hands-on demonstrations, works in progress, social events, and the amazing California coastal environment. So I hope that you will. I hope that you will join and pack your surfboard in your station wagon and come out to Santa Barbara. Look forward to seeing you there. Thanks, everybody.